So welcome back. So the part 2 of this lecture is going to be on feedback control and optimality, right? Like I said, basically the open loop control does not have these stability and things like that, but it can be solved through numerical methods very well. Whereas if you want stability, typically feedback is necessary, and I'm going to basically first consider the simplest of those cases, which is the linear control problem, just for us to understand the issues, right? So we will consider the standard x dot equals ax plus bu, and we'll assume ab is actually stabilizable. I say controllable, that's too strong an assumption. Ab is stabilizable, which implies that there exists, I mean, it's the same thing as k such that a plus bk is Hurwitz, right? And basically let k be the set of stabilizing controllers, that is all k's where a plus bk is Hurwitz, right? So we're going to define performance cost j, okay, in terms of these parameters r1, r2, and then we will specifically assume that the feedback control is actually linear control. So u is some k times x, where k is belonging to this script k set, right, the stabilizing controllers. And the performance cost is j of x0 comma k is given by this integral, the quadratic cost, where and we can state that basically this cost can be computed through this simple quadratic function, which involves this matrix P, where P is positive definite solution to this equation. So again, I mean, something that we have seen, I suppose, but I want to remind yourself how this works. So we have j is equal to integral x transpose r 1u, sorry, x plus u transpose r to u, right? U is kx, so that gives me x transpose r1 plus k transpose r2 k times u and integrals, right? 0 to infinity, so this is x dt. But x dot equals a plus bk x after you substitute u equals k. So therefore x of t is e raised to a plus bk times t x0, right? So I can substitute that as x0 transpose times 0 to infinity e raised to a transpose t plus r1 plus k transpose r2 k times e raised to at dt, and this whole thing times x0. The claim is basically this is a well-defined integral, and therefore I'm going to give it a symbol called p. And much more, if r1 and r2 are positive definite, or at least r2, one of them is positive definite, I mean r1 specifically is positive definite, then this can be shown to be positive definite. The second aspect of it is, sorry, this is a tilde, where a tilde is a plus bk. Okay, So since this a plus bk is Hurwitz, this is kind of going to 0 as t tends to infinity. So this particular integral is well defined. We have seen this before. Much more than that, we actually showed that if I take this p and then do this a tilde p plus p a tilde, okay, then that will be nothing but this, right? How do I know that? Basically, when I multiply with a tilde transpose, then basically plus p times this whole thing times a tilde, we will essentially have something like a derivative d by dt of e a tilde transpose t r tilde, let's say this is r tilde, right, e a t integral 0 to infinity, okay. And when we integrate this, basically at infinity, that's going to be 0, and this is going to be simply this particular quantity minus r tilde, right? So we have seen this one without any control before, and I'm just repeating that argument so that you understand this, right? So essentially, therefore, it becomes a standard optimization problem. We want to minimize this particular quantity right, which depends only on P, and that satisfies this particular quadratic equation. Essentially it's a bilinear equation in P and K. If you recall, basically for finding stabilizing controllers, we had this bilinear equation in which we actually transformed that into a joint equation, the corresponding dual equation, and we could actually rewrite that as a linear matrix inequality, and we therefore could solve the stabilization problem through that. Whereas in this particular case, basically we'll pose this and then constraint optimization problem, and there is nothing like Q of t or anything like that. So there is nothing calculus of variations. This is actually straightforward classical optimization, right? So the solution to this happens to be K equals minus R2 inverse B transpose P. Not surprising that it looks very similar to what we have seen in the time varying case that came from Hamiltonian formulation, and the P is going to satisfy this particular quadratic equation, which is known as algebraic Riccati equation. Okay, now I want to shed some insight into this particular problem, right? So what we have is minimization of X transpose P X0 subject to A plus bk transpose P plus P times A plus bk plus R1 plus k transpose R2, k is 0, right? Now, since we look at this particular constraint, this is actually a matrix constraint. It's a square matrix constraint, but if you pay a little bit close attention, it's actually a symmetric matrix. So in other words, basically, except the diagonal, everything is repeated twice, right? So half of it is actually repeated information. So Lagrange multipliers, we need not have all of them. Or alternatively, I can actually imagine a Lagrange multiplier also put in a linear matrix format. So so essentially, I can think of my Lagrangian, which is going to depend on my basic variables P, K, and going to be a Lagrange multiplier, and I'm going to say that that's also a square matrix Q, symmetric matrix for that matter, which is going to look like something like this. And I'm going to write a of trace. Okay, there's no special reason beyond that. Everything else is so. Q times this nasty equation. Okay, so this is my Lagrangian. So, and then of course the next question comes is basically, why did I pick this trace and things like that. With a little bit of work, every matrix equation can be written as a bunch of vector equations, and and you can take the thing like lambda transpose that vector equation and basically rearrange it in such a way that it looks like this Q times this same equation, in which case the trace becomes that lambda transpose the entire equation. So we are actually consistent with the standard vector optimization, except once we get the hang of it, we can actually solve this as a directly matrix equation. And of course, there we know how to take derivatives with respect to vectors. Here we have to know how to take at least some of these things, derivatives with respect to matrices, right? So if I'm not going to really show much more than what is needed here. Basically, if I take this entire thing with respect to K, what I'll end up with is the following. Basically, so B transpose PQ, one of the equations, when I set take the derivative with respect to K and set it to 0, I'm going to get some equation like this. Okay, is equal to 0. Okay, so if somehow I'm lucked out, then Q happens to be positive definite, then K is equal to minus R2 inverse B transpose B, which is what the optimal controller that we're going to get. So under what conditions can Q have positive definiteness and things like that, and we can actually show certain things about this formulation by setting the derivative with respect to P, and we can show that that will be actually an equation that involves a similar equation, but it's an adjoint equation, and because A plus BK is already assumed to be stable, Q is going to be positive definite and things like that. So we have all these nice aspects to this particular problem, and once we substitute this K in this particular equation, then we end up with this algebraic Riccati equation, and this is really a celebrated equation. This is so-called linear quadratic regulator, and like I've said earlier, basically this also generalizes when we have actually noise and things like that, and that's equivalent to solving some H2 norm of linear system, right? So, but you get the idea. This is a very different method. We are actually solving the problem for all stabilizing controllers, but minimizing a quadratic function that looks similar to what we have seen in your optimal control, the open loop optimal control. So this is one of those things where you actually married the optimal control Hamiltonian type of formulation or Euler Lagrange equations to stability. So you combine these two, and then we get one single kind of framework where we solve both the problems at the same time, right? So that's the linear case. So I'm going to look at the nonlinear case, right? So in the nonlinear case, again, we will assume that x dot equals f of x comma u. There is no advantage of picking f of x comma plus g times u, the affine version that we've been using many times. So, and then basically the cost function, just like we had a quadratic function in terms of x and u, here I'm going to use L, that is both function of x and u, right? And like set of stabilizing controllers K, here we are going to assume u is some function that stabilizes it. What that means is asymptotically it takes the system to 0. Actually, I should have said it's anything that takes the state to 0, right? Like before, I'm going to define my Hamiltonian to be L plus P transpose f of x comma u. Okay, don't bother. Basically, I'm just defining something, right? But here is the result. Assume there exists a radial unbounded function. You can clearly see where that is coming from. It's coming from the Lyapunov stability notions, and a feedback controller phi of x, okay, such that v of 0 is 0, vx is positive definite, and phi of 0 is 0, and this v dot part is less than 0, and something different. H basically satisfies an equality, and then h of x comma u comma v prime is going to be greater than or equal to 0 for all u. Then the conclusion becomes basically the cost that the optimal cost is going to be exactly equal to this Lyapunov function evaluated at x0, and that cost is going to be sorry, let me rephrase this, right? So this phi of x is some feedback control. At that feedback, the value it is going to be exactly equal to the Lyapunov function, which happens to be the value function that we saw in the open loop control, and this is going to be optimal function, which is going to be less than or equal to minimum of this thing. So again, like I said, this is kind of a marriage between your open loop optimal control, and this is an infinite horizon case where we desperately need stability in terms of a feedback control. So this is combining all those notions, right? So I don't have to show you that this particular system is such that the phi of x is actually going to stabilize, right? Simply because, let's see. So what we have is x dot equals f of x comma u, right? And we are assuming that phi of x and v of x are such that v of 0 is 0, v of x is positive definite, positive, right? And phi of 0 is 0. Ignore that, it's not a big deal. And much more, basically we are going to say v prime of x times f of x comma phi of x. That is, instead of u, I'm going to pick this u to be phi of x, the feedback control, is less than 0 for all x non-zero. So in that sense, this particular dynamical system with u replaced by its feedback implies zero solution is asymptotically stable globally if you have radially unboundedness, right? So that's what is the first part of the result, right? The second part of the result, on the other hand, is something to do with Hamiltonian, and I'm going to show you something interesting there, right? So recall that so v dot of x of t for some u, right, is nothing but v prime of x of t times f of x comma u of t. Okay, we know that. So I'm going to add L and subtract L. But we know that this is nothing but h of x comma u comma v prime, right, minus L. So rearranging this, basically I'm going to get L is equal to v dot, sorry, h minus v dot, and I can integrate this. Integral L is integral h minus integral v dot. This of course is nothing but our j, which is going to be j of x0 comma u, okay, for an arbitrary u, right? And then what do we know about integral of v dot from 0 to infinity? Of course, that's nothing but v of x0 minus v of x of infinity plus this integral h, right? But what do we assume about u? For all stabilizing controllers, meaning stabilizing functions that take the state to 0, basically this part is going to be 0, right? V of 0 is 0, so this is going to go to 0. So, but then what did we assume about h? H, the only assumption that we make is h is greater than or equal to 0. So that therefore this is basically going to be greater than or equal to v of x0, which because of the fact that h of x comma phi of x is 0, then basically that can be shown to be, by reversing the same argument, this is true, right? So perhaps should look at our textbook and then basically see how this works out. But essentially, the first few parts is something to do with stability, and the Hamiltonian that is brought in, and basically just by assuming that h is 0 at the optimal control and it's greater than or equal to 0 for every other u, we can actually get optimality for free, and then the cost function can be evaluated at phi, or for that matter at any u, as v of x0, right? So that's essentially your optimal nonlinear feedback control. And perhaps at a later point I'll show you some of the examples towards the end of the class, how some of these things work. As a theory, it's quite good to see, and it specializes to linear controllers and all those things. And then we have generalized in the case of how it works for robustness or disturbance rejection and things like that. We'll see some of those results. A lot of times, basically, we end up using these results for still very special classes of systems rather than a generic problem, because it's very difficult to find all these v's and phi's and things like that. But the theory is there, right? And so when we come back, we will actually look at some very important topic called stability margins. So we have all these nice theories, and then we have way of solving the stability problem, optimization problems. The open loop, anyway, we don't have any hope in terms of basically allowing for uncertainties. Whatever it is, it does, right? Whereas the feedback control problem, can we actually get some margins? Can we actually get some robustness guarantees for the optimal controls that we developed, right? So, and that's what we're going to look. So Why is that important? Well, when we are designing controllers, basic things are taken care of. We optimized the cost, we optimized, we ensured that the feedback controller is stable and things like that. But beyond that, can we actually get some robustness for the, these controllers, right? And so therefore we need to define stability margins. They are defined for linear systems very well in classical literature, but we will take a stab at it for nonlinear systems, and then show for the optimal controller that we just saw, we can actually get margins in a certain special case. And if we pick the cost to be some kind of quadratic looking function, for that particular case we can actually show that there are margins, right? And in fact that specializes to very classical result on linear quadratic regulators having certain margins. We will discuss first a little bit about basically importance of margins, and then different types of margins, gain, phase, and how they are important in various scenarios, and also introduce this strange notion of disk margins, and then show that optimal regulators will eventually have all these things, right? What does this mean? Eventually, suppose we cannot solve this particular problem through all these very difficult equations, can we actually do something else? Can we actually get inverse optimality? If we have a stabilizing controller, can I know that there is some cost that is going to be minimized for that particular controller? At least that will shed some insight in terms of what we are minimizing. And moreover, can we actually somehow get some stability margins for that kind of approach in terms of can we pick, within the feasibility, can we pick a controller that actually gives margins also, right? So that is a different approach. That's in a way an approach that avoids the difficulty of solving these very difficult equations, directly attacking basically getting controllers that have stability margins, but then as a side we can actually show that they have some kind of cost that is getting minimized, and that may help us understand how these things work, right? So with that, this lecture 2 is complete, and then when we come back we will start with stability margins, and then go beyond that to disturbance rejection, and then basically combine some of these disturbance rejection or robustness with optimization, and that will come to an end of this particular course. And then we will follow with some advanced topics that we never covered here, some of the things that we should be looking forward to. Thank you.